Section 3.3 introduces the idea of a line of best fit and linear models of scatterplots. A scatterplot itself has points that show the relationship between two sets of data. These points are not going to be connected, but if there is a potential linear pattern, then we can use a line of best fit, also called a trend line, and it's simply the best fit line that most closely resembles the two sets of data. And this can be used to help us make predictions inside or outside our set of data points. We use the word correlation to determine how well an equation for a line of best fit matches the scatter plot, and this determines how strongly the data are linked together. As you can see below, there are several types of correlation. In this graph, this is actually perfect correlation since all of the data forms a perfectly straight line and it would have a correlation coefficient of 1. In the next graph, this is considered a high positive correlation. So notice the data is not perfectly linear, but it does follow a linear pattern. As x increases, y increases. And this would have a correlation coefficient of 0.9. In the third graph, this would be considered a weak positive correlation. So there is some correlation that as x increases, y also increases, but it's not as close as the previous two. This would have a correlation coefficient of 0.5. The very center, we'd say there's no correlation. So in this case, there's really no linear relationship between the inputs and the outputs. And then on the other end of the spectrum, it's just a repeated pattern, except now we have negative correlations. So we have weak, we have high, and we have perfect. And the difference is that to be negative, as x increases, y decreases. In example 1, the local ice cream shop keeps track of how much ice cream they will sell versus the noon temperature on that day. The figures of the last 12 days are shown in both the table and the scatter plot. It is easier to see in the scatter plot that the warmer weather leads to more sales, but the relationship is not perfect. However, we would say that this has a positive correlation that is fairly high. In this case, we want to create a line of best fit to help us make some predictions. So we're going to draw a line, and this line models the relationship as closely as possible. Now see, we can estimate the equation of our line by using 2 points that follow in the line. These points do not have to be actual data points from the table. So in my case, I'm going to choose this point, which notice is not an actual data point from the table, but then also this point, which is data from the table. I'm going to label the coordinates of each. Then I'm going to use these 2 points to help me determine what the slope of this line is, also known as the rate of change. So to calculate that, I'm looking at the difference in ice cream sales, so 325 minus 250, and those are both of my y values. And then I'm looking at the difference in the temperature, and those are my x values. This simplifies to $75 over 2.4 degrees. And if we want to write that as a unit rate, that is equivalent to $31.25 for every degree. And remember, this just means that for every degree the temperature rises, the ice cream sales will increase by about $31.25. Now, if this is our rate of change, we also have to calculate a starting amount that will produce this line. So our starting amount will always occur when x equals 0. And that produces our b value. So in this case, I can use x, y, and m to help figure out the value of b. So the sales should be 250 when it is 14 degrees outside, but there's some starting value to make this true. So if I calculate this, it simplifies to 250 equals 437.5. And then solving for the value of b means I have to subtract that quantity from both sides. And therefore b would equal negative 187.5. And that is our starting value. Now, in this context, it doesn't quite make sense to have a negative number of sales at 0 degrees, but this is the value that produces these sales for these corresponding temperatures. One thing to keep in mind with scatter plots and lines of best fit is they're most useful for values within our data range, and that's why a temperature of 0 degrees wouldn't make as much sense here for a prediction if you take a look at what the temperature of our actual data is. Nevertheless, we could still use this B value to make predictions about temperatures that fall within the current values that we have. So y equals 31.25x minus 187.5. In example 2, the scatter plot below shows the relationship between the number of video files x stored on a computer and the number of gigabytes y of storage space available on the computer. So as we can see, as the number of video files increases, the available storage will decrease. So this is going to have a negative correlation that looks pretty strong here. So we start by drawing a line of best fit that most closely resembles our data. Once we have our line, we are going to choose 2 points on the line once again to help us create the equation. So I've chosen this point and this point, and the coordinates of these are 4 and 198 and 10 and 150. So to find the equation of the line, I need my rate of change and my starting point. To find our rate of change, we need the change in the available storage. So 150 minus 198. As you can see, this went down by 48 gigabytes. And the change in the number of video files would be 10 minus 4. So this was an increase of 6 video files. So adding an additional 6 video files decreased the available storage by 48 gigabytes. That means our unit rate should be about 8 gigabytes per video file. So we can use one of our points to help us figure out what this starting amount is of available storage on the computer. If we think about it, when there are 4 video files, there's 198 gigabytes left. So if we add those 4 files back, that would be a total of 32 gigabytes. So what this actually looks like is I'm multiplying my rate of change by 4, And in reality, this amount gets subtracted from the starting amount of available storage. But if that's what I'm trying to find, then I can take this quantity, which is negative 32, and add it back to the available amount of storage. And this now tells me, get rid of this line, this tells me that the starting amount of storage was 230 gigabytes. So once again, I used a piece of data to help me figure out what my starting point was, but I also had to incorporate that rate of change to figure it out as well. Therefore, my final equation would be y equals negative 8x plus 230. And I'm supposed to use this to predict how much available storage there is for 5 video files. So I simply substitute 5 for x. If I'm using an average of 8 gigabytes per video file, then for 5 video files, I'd be using 40 gigabytes. So subtracting that from the 230 tells me that there would be 190 gigabytes available when using 5 video files. At this point, go ahead and start working on your practice questions. Notice the first two, the first problem, you will be drawing a line of best fit and then finding the equation, just like we did in example 1 and example 2. For question number 2, you can draw your line of best fit and then just use that line on the graph to predict the points someone will have after 8 games. For the rest of the questions, they are all multiple choice. So use your best judgment on these. These questions do slightly resemble keystone questions, so it's important that you take your time and really think about them.